Okay, so hello and welcome again. We are on the second demo for our setup for a Fresnel equation and Brewster's angle. This is the second demo in the series of optics demos. And what we have here is the same setup, and it's exactly like we started out first time. So we have a helium neon laser, a polarizer with a microscope slide hitting this guy, and which is a photodetector one, and going on to that one. So in this case, we would do the reference measurement later. I haven't done the measurement yet, but it's at the Brewster's angle and it's parallel polarization. And we would now switch this guy to rotate the polarization so that we get perpendicular out. And we'll do the same experiment as we did last time, but we'll do it with perpendicular polarization so that we can plot the Fresnel equation curves for perpendicular polarization. So I'm going to rotate the polarizer so that my channel 2 with the photodetector right here goes gradually up to the peak power. So I rotate that guy to the peak power. Now remember, the same thing could be done by just looking at the angle on the dial and adding 90 to it, but I'm just doing it this way to get a experimental outlook to it. So now I have relatively high power. It's at the peak. Channel 2 is 5 volts per division. All we are concerned about is that it's at a peak value, and so what we do now is we measured the transmitted power from 0 to 90 degrees over here. So I'm going to move this guy right down to 0. So now we have perpendicular polarization hitting it at 90 degree incidence, or 0 degree incidence rather. And so the power hitting my photodiode is about 10 volts. This is photodiode 1, this guy right here, sitting at 10 volts. And we are gradually going to increase the angles from 0 to 10 degrees, 10 degrees to 20 degrees, just like we did before. So at 10 degrees, my voltage is again around 10 volts. It's a little less than 10, it's around 9.5. At 20 degrees, so it's still sort of 9.5. It's less than the previous one, but it's at 9.5, 10, whatever you want to call it, at 20 degrees. At 30, we have about 9.5 again. So it's gradually going down. This will eventually go down faster as we go to bigger and bigger increments. So at 40 degrees, we have 9 volts. At 50 degrees, so we have around 5, 6, 7, 8, 8.5 volts. At 56 degrees, or the Brewster's angle, we have 5, 6, 7, 7.5 volts.
at
60 degrees. We still have 7.5. We're still in that Brewster's angle range. At 70 degrees, we have 5.5 volts. So now we are rotating that to 75 degrees. So now we have right there, we have around 4 volts right there. So like as before, we have channel 1 has 5 volts per division. So we have 4 volts right there at 75. At 80 degrees, we have it down to 0.12, around 3 volts, a little less than 3 volts at 75. Sorry, at 80 degrees. My mistake. It's probably been a long day. At 85 degrees, we have almost down. We're close to half a volt right here. So this is where it went down, and this is the trace coming in. It's like almost close. It's like a little less than half a volt. Less than a volt. It's close to half a volt, something like that. We do a final measurement of 87. So at 87 degrees, it's barely distinguishable from zeros. So for all practical purposes, it can be taken as zeros. It's like even less than half a volt right there. So that's the angles. Before we stop, we'll come and see the grazing incidence again. At the grazing incidence angle, let's take a closer look at the photodetector side. We have the reflected beam spot very bright. It's like a very bright spot, and that also shows that for this case also we have a high amount of power reflected and very small transmitted because of the grazing incidence phenomenon. So before we turn our video off, we are going to look at the power when I remove the microscope slide. So I remove that. So right now all my power for the perpendicular polarization is hitting channel 1. So that would give me the reference power. So the reference power for channel 1 is around 11 volts. Ideally, that should correspond to the right ratios and everything, but it depends on practical errors and everything, and I would like to specify that if this kind of experiment is being done for a research grade data acquisition, you would need piezoelectric stagers and micropositioners, nanopositioners on the works. Basically, this is for classroom demonstration purposes, so we do have some errors in it. So for perpendicular polarization, we have 11 volts hitting it. That's our VREF. So V1 over VREF will give us the transmission power coefficients. For perpendicular polarization, if you want to do the reflective power coefficients, we do 1 minus T, where T is equal to V1 over Vref. The 1 minus T gives us R, and then we can plot them with respect to theta or theta in the x-axis, and they'll give us the Fresnel equation curves. So that was the second half of the experiment for Fresnel equations in Brewster's angle. I'm Julius Charity. Thanks for watching.